Okay, in the last class, I was defining partial trace. So I will start with that. Okay. So we define, let me recall. So if we have two Hilbert space, so we will slowly shift to the notations of the, I mean, I was using operator algebraic notation, which was comfortable so that I will not make a mistake. But we have to slowly, I mean, for example, to completely positive map, we have to write it like this, theta or n or whatever. The book it's called n. A going to B, that means it goes from there. And all these things, the system, all these things we have to represent in that notation. We will start doing that. But for the time being, so we have two systems, two Hilbert spaces, HA, HB, okay, of dimension, with dimensions DA and DB. Okay. Suppose if we have a matrix, if you have a matrix in L of HA, which is just MDA, MDA cross DA matrices, that is what the operators in HA, then you can trace it just the sum of the diagonal things, or you can define it through linear functional. So if you have a X in, so usually this is called, you write it as AB, so that it is from A to B kind of thing. It is in L of HA. I mean, when you write like this is like tensor, like a product. Product means it's tensor. When you write XAB or even HEAB, when you write sometime HEAB, we will write, which is usually HA tensor HB, or you write IJ, which means I tensor J. I is the 0 to, I mean, if you have a DA dimension Hilbert space, then 0 to DA minus 1, we will denote the standard basis by numbers. Just instead of EI or something, we'll just denote it by I. So if we have XA in HA tensor HB, which is just an operator from HA tensor HB to HA tensor HB, then you define a linear functional. So let me denote it as this. P is a linear functional from LA HA C by P of XA equal to trace of, I take XA tensor 1 and take the product with XAP. Okay, this is a linear functional. And this is, so this is a linear functional L of HA. L of HA is a metric space with respect to the trace inner product. So by Rees lemma, we have to get an element in L of HA which implements this linear functional. So there exists, I mean, I will call it YA. I will call it YA. I mean, I'll change the notation. Okay, YA. I hope you will have no confusion. You call it as trace B of X. Okay, which is what I want to call it as YA or something. So this is an element in L of HA, L of HA. Okay. L of HA, such that this is an operator. Okay. Trace is usually number, but you trace out only B, this Hilbert space with respect to this Hilbert space, then you get with respect to that system, then you get this operator. So which is a, so such that trace of, so this is the usual trace. When I put a subscript for the, this is what is called partial trace. Okay, trace of one tensor. Yeah, this is XA in the first one. XA tensor 1 XAB equal to trace of XA. This is the trace on L of HA tensor HB. This is a trace on L of HA. Okay, but I write trace for everything. If I put a here, it will be confusing with that, okay, with the partial trace. So XA times this is trace of B of XAB. Okay, no confusion. Okay. So this is what is called partial trace with respect to HB or whatever. Okay. With respect to HB. This is a analog of what is called conditional expectation in probability. Conditional expectation is with respect to some sub-sigma algebra. You have a bigger sigma algebra, your functions measurable with respect to that sigma algebra. You have a sub sigma algebra. Then you have the conditional expectation. Okay, so which is like actually a projection. If you have a sigma, say conditional expectation is if I mean conditional expectation is defined for non-L2 function also, but for if you take L2 function, this is something with respect to omega with respect to some sigma algebra. Then you will have a sub sigma algebra of this. Then this will be a projection from here to here, right? That will be the conditional expectation. Okay, I mean this is for L2 function, but that can be generally for generalized for any measurable function satisfying some condition. This will precisely satisfy this trace is like integration. I mean, just to give them, we don't need all that. But I mean, this trace is like integration, and this partial trace is like conditional expectation. Trace is like, for example, expectation. Integration is expectation. Partial trace is like conditional expectation. Conditional expectation from this algebra to this algebra. Okay, that is what it is. So those algebras are the quantum probability spaces here. So this is just the conditional expectation here. I mean, we don't have marginal and other things here because we don't have sample space, we don't have measure and all that. So we have to talk about this. This is, I mean, in classical probability, you have marginal and other things, okay, which we don't have. Similarly, we can define trace A of any x to be defined Ax by this is for all x, right? This is for all x. This relation is for all xi. Okay? Similarly, trace xab for ab here by trace of one tensor yb, okay, yb xab equal to again the trace of yb and the trace a of xab. Okay. So this is partial trace with respect to the first component, the system A. Okay. So we can, so this is just to show that it does not depend on any particular representation or something. But for us, you can see that, say, the one thing you can see is if you have the trace on one of the system, A or B, okay, let's say this is the trace on B, okay, then one tensor trace, this acting on one tensor trace acting on, I want to say that this is nothing but just one tensor trace, okay? That is because one tensor trace of trace, trace on this is just trace tensor trace. If you just look at it, it's just trace tensor trace. It is just you take the diagonal of those things, and this is just basically trace tensor. Okay, so partial tensor is nothing but one tensor. This is trace. It's nothing but one tensor trace. So if you want, you can. This is because, you can verify that this satisfies this because trace of one tensor trace is actual trace, the original trace. Where you have to see that this trace is on HB, and if you take the trace that is on HA, you will, once you apply this, you will get the operator on HA. Then you have the trace on A. I don't want to write A here because that will confuse this notation. Okay? So if you apply the trace of one tensor trace is actual trace on the bigger one, HA tensor HB, L of HA tensor HB. Okay? So because of that, this is just one tensor trace. Okay? So if you have a matrix Xij in L of HA tensor HB, okay, then trace B of Xij is just trace of Xij. Okay. Trace of Xij will give a scalar. This is a n cross whatever dB cross dA cross dA matrix. Okay. But this is a matrix with Xij. All these Xijs are in L of HB, right? And but this is scalar. This whole thing is in, this is a dA cross dA matrix. Usually, this is number. This is complex number. Okay. So on the other hand, what is trace with respect to the first entry. So we can also define to be like this: trace of B of any x a b equal to, see, if we have two Hilbert space H tensor K, we have two Hilbert space, there is no way, there is no canonical way you can embed H into this. You have to, you can embed it like this. If you have a xi in H, then you can write it as xi tensor something here. You fix a vector and you can write it here. That's not canonical. Theta is not canonical. But if you have matrices, if you have operators, then there is something called identity operator. Okay? You can embed this L of HA into L of HA. This is what is called amplification, L of HB, as x going to x tensor 1. You can write it like that. Okay? So, but you can actually embed a Hilbert space tensored with the L of that. That's also a Hilbert space for us. Okay. So you can trace of XB is nothing but you have this I. I mean, this is where this I equal to 1 to D. This is with respect to B, no? So dB minus 1 is Y and B for HB. So this is 1 A tensor this. Even though it's a vector, you can consider it as a row matrix and you can write it like that. Okay? X. Then you have 1A tensor I. Okay? Here this is summation. I equal to 0 to I equal to 0. Sorry, it's not 1, it's 0. I equal to, it starts with 0. Okay? I equal to 0 to dA minus 1. dB minus 1. Okay? I mean, it starts with 0, not 1. dB minus 1. So you can write it like that. Okay? Okay. If you do the same thing, what is trace A? Can you guess what is trace A of any x? Where if x is going to look like xij. Okay? Where with, I mean, x is going to look like xij with xij's or matrix. I mean, if you have x's in xij, then trace B is just trace of xij and you get a whatever dA plus dA matrix. So when you have something like this, what is trace with respect to A? That will be just summation of all those matrices. That will give a matrix. Okay? Trace AX, trace x is equal to this is in L of HA tensor HB. Okay? Then trace of x is equal to, if x is like that, then summation over xi equal to whatever. I equal to, I mean, it starts with 0, I equal to dA minus. It's only the diagonal matrices. I mean, diagonal entries, which are matrices. Okay? This is precisely, I mean, this, you can check, I mean, you can verify it by using this formula. Trace of A of any x, which is equal to trace tensor 1. Okay? Which is trace tensor 1. And this is equal to of any x, trace tensor 1 of any x. Okay? If you want, you can write it, I mean, you can verify that. I mean, you can verify it by substitution and that this is equal to this. And this is going to be, if you want, you can write it as, ij tensor x or whatever, but you can directly get it also. This is equal to summation I equal to 0 to dA minus 1 of, so this is a trace here. So I tensor 1 of x, I tensor 1. Okay? This one is in HB. Okay? Is okay? Here, trace is just, I mean, this is just, you can directly verify it if you want. You will get it, number one. Trace, what is trace of any x for a general x? This is just trace of I, x, I, right? I runs over orthonormal basis and you over to D minus whatever, runs over orthonormal. Okay. If you have one tensor trace, this is just definition of one tensor. One tensor, you have one tensor, you get the trace of. You can verify for a linear functional, you have to verify it on a linear spanning set, and the total set, okay, total set. So you can verify it on the elementary tensor that this is satisfied. That's all. That's all. Okay? So that's why. So similarly, that's why I have written similarly. Similarly, this is similar to that, except that it is in the first component. Okay. Okay. So if you use this, you will get that. That is precisely this. Okay? If you use that, if you use this formula, act it on any x on this, then if you just apply this, okay, let me just verify that. If you want to apply this, I tensor identity, okay, identity on the identity are one. I may write identity on one. I mean, both are same, okay? Identity on one, acting on any x, then you have this I tensor. I'm sorry. I want to write this. I want to write this. 1 HA tensor. I want to verify this. Verify which one? What I have written there, no? That one. If you want to verify this one, that I am doing. Okay, you can directly verify, or you can use this formula. Okay? This is basically because of this is one tensor trace. Okay? 1 HA tensor, this I, then you have a x, and 1 HA tensor, this I. Okay? Summation over I. What is this element? This is this element. This is a diagonal with I everywhere. Okay? That is what 1 HA tensor. If you have two matrices, x and y, x tensor y is going to be the entry of this, entry of that in the corresponding II, JJ entry. I mean, whatever. Okay? So this will be diagonal this vector, I vector, and that will be diagonal that vector. Okay? So finally, you will get what you get here is summation over I. I mean, summation over I. You get all those things. I mean, I Xij. Okay. I mean, whatever, Xij is a matrix. Okay. Here there is a problem. This I is different. Okay. This Xi, this is the entry, Xij entry. Okay. I mean, this I is a summation I. This I is okay. So I call it I prime. Okay. Summation. This is for the trace, summation I prime. I prime, Xij, then I prime. Okay. You can take that because it's linear, you can put the summation I. All those things. This is precisely trace of that. That's all. This is precisely trace of I, Xij. Okay. Okay. Similarly, if I want to compute the trace of this, this is trace B. Okay. This is trace B. Okay. Similarly, if I want to consider trace x of A with respect to A, okay, I have to do this. I have to compute this. I in the first one, tensor 1, okay, summation over I maybe I prime, we call it I prime, I tensor 1, okay, x I tensor 1. Okay. What is this matrix? I tensor, this is 1 in HB. Okay. What is this matrix? This, I mean, if you have anything tensor 1, okay, this will be this what this I is just the ith. I mean, this is just a number. This is I is the vector with 1 at the ith place, everywhere else 0. Okay, so this will have a row of matrices. This is a row of matrices. Okay, within the ith place there is identity. Instead of 1, there will be an identity. This is also a column of matrices. In the ith place, it is 1b. So if you compute all those things, you will get a matrix with I x I mean, it will be in the ith place. I mean, but this is matrix multiplication, right? So it will be Xij EI, this is what you will get. Okay, you understand? This is a, this is, I mean, you are taking this row and going to multiply that corresponding column here. So this will be this, right? Okay, this is what you will get. Okay, I mean, this is the ijth element of that matrix. Okay, so I mean, this is of course. Now you just have to compute the trace of that, which is just going to be no, there is no. Yeah, wait. let me write it. Okay, this is going. Let me just write it. No, this is just going to be 0, 0, 1 at the ith place, 1b. Okay, and you have xij. Okay, you have xij, and you have, so if you just multiply it, it will multiply on the left. Oh, there is just one. There is no I. Sorry, it is just, you just multiply in the left. Okay, so what will you get? That is right. That is right. You have the summation here, no? Summation I prime. You have summation I prime here. So you are supposed to get a single matrix, right? You will get supposed to get yeah. Wait a minute. You will just get xi. That's what you will get, right? I mean, if you further expand this, it will be easier, but then multiplication becomes messy. You can further expand this with matrix units and other things. That will become messy. So you have one at the ith place, and if you have a, I mean, if you have some matrix here, one at the ith place, and if you have a matrix here, so it will select the it will just select the ith column, right? I mean, it's just the, so, and if you again multiply with something like that, you will basically get you will just get xi I prime. This is what you will get as a matrix. Okay? Now summation I prime. Anyway, check. Okay. I've done it once in my life, but I think I'm sure it's correct. Okay. Okay. So this is what the trace B of this. Okay. Trace A of this. Oh, I didn't change this. Sorry. You can look at this. Okay. So this is about partial trace. Okay, then I want to write the following. Let me write, I mean, when we do those calculations, let us better do something about completely positive and go back to this again. I have to prove, I have to define something called partial transpose to for the next theorem. So before that, let us make this. So the following two things are equal. If we have a phi from, okay, let me write it, L of HA to L of HB. Later, I will change this to script n or something. I will come to that later. For the time being, I'll write phi. Okay, phi is from HA to HB is CP. Okay, this is equivalent to saying there exists an isometry U from. I was stating this last time. We stopped in the middle. So there is an isometry from HA to HB tensor another HC. Maybe HC tensor H this way or that way, which way I want. Let's see. I don't know whether HC tensor HB or I think this is okay. Okay, HA tensor HB. Okay, such that phi of x in, of course, x is in A. Okay, this should land up in B. Okay, This should land up in B. So you take XA, U star. U star will bring it any HB tensor HC to HA. Okay. And then U, so this will land up in HB tensor HC. Then you take the trace with respect to C. Okay. We have already noticed, I think we have already noticed that this partial trace is a completely positive map. Okay, this is, I mean, I gave a more general assignment. Instead of a trace, you have one tensor phi kind of thing. Okay, that's a completely positive map. So this is just this is a homomorphism. Okay. So what this says is if I have a completely positive map from HA to L of HA to L of HB, then from L of HA to L of HB, this is a homomorphism. You get a homomorphism and a bigger one, okay, and every homomorphism will look like this, okay, in B of H. Okay. So I mean, not in general phenomenon zero, in B of H. So up to that, then you take a partial. This is some sort of dilation. This is what is called Stein spring dilation. Okay, this theorem is Stein spring theorem, such that this happens. Okay. So this is what we want. Okay. One way is clear. Of course, this is CP. We have already proved that this is a partial trace is a CP map, and this is a CP map. Homomorphism is CP map. We have proved. So the composition is CP map. So this way is proved. So we only have to prove this way. This way. I forgot to say it's a CP, not CP. It's a quantum channel. CP. It's a quantum channel. Sorry, that is CP plus trace preserving. Plus trace preserving. So phi is CP. This implies then so there exists V1 up to VD. Okay. VD or from HA to HB such that P of X equal to summation Vi x Vi star equal to 1 to D. Okay. So this we have proved. And further, P is trace preserving. So this implies trace of P of X equal to trace of summation Vi x Vi star, okay, which is equal to trace of X. I mean, this is equal to same as saying that summation, you can take the sum out or you can keep it inside, doesn't matter. You can take the sum and then turn it around and bring it back here. Okay. You can take the sum. In the trace, you can bring this element to here. But since you have a sum, you need to see, you can take the sum out, take it there, and then bring the sum inside again. Okay. So this is same as X Vi star Vi, okay, summation of this. Okay. So this is equal to trace of X times summation Vi star Vi. Okay. Which is Hilbert-Smith inner product of X, maybe X star, doesn't matter. I mean, this is Hilbert-Smith inner product. X star here, no? X star, whatever, X star. Doesn't matter. This is true for all X. Okay. X star times summation Vi star Vi. Okay. This is equal to, by the condition, this is equal to trace X. So, which is same as X star inner product with 1. This is for all X. For all X, something is true. Some inner product is true means that has to be, this has to be equal to that in inner product. So, this implies Vi star Vi equal to 1. Okay, whatever. So, okay. So now we have got a V1 up to Vd such that summation Vi star Vi equal to 1. From this, we have to get the isometry. So let H C equal to just CD. Okay. So you HC equal to CD. Now we want a map from HA to HB tensor CD. So but we have map from HA to HB, so I will change this. Okay? I will take to CD tensor HB. Maybe there also I will change. I change here HB, HC tensor HB. And return HB tensor HC tensor HB. Okay. This is CD. So we want a map from here. Okay. So this is just a vector, D vector of elements coming from here. Okay. So we want a map from here. We want a U from here. So define, so I just define U to be just this. Let me just write it. V1 to Vd. Okay. This is I mean, VIs are D, it's from HA to HB, right? So that should be DB cross DA, right? VIs are DB cross DA matrix. Okay? I mean, just to make sure, these are all DB cross DA matrix, and there are D of them. Okay, so this is going to be DB cross DA times D. Okay, so this is from we want from HA, right? So this is like 1 tensor DA, 2, 1 tensor DA, it should be a row vector or a column vector. It should be a, yeah, this is okay. This will take a HA, maybe I should write it as a column. Yeah. So there I have, once again, let me see. There I have U star there. Then, okay. Okay, U is column. Okay. V1 up to Vd. Now it makes sense. Okay. Each V1, okay. Yeah. And there are, yeah, it will land up in dA times D vector space. Sorry, dB times D vector space. I mean, it will act on dA dimension. It will act on dA dimension. It will land up in dA times D, dB times D. That's what we want. So this U is a map from HA to HB tensor CD. That's what we want. Okay. Now it's correct. Now it's correct. So now we have U star there. So now U x U star equal to V1 up to Vd. Okay. X V. So Ux U star, right? That's what Ux and V1 to Vd star. Now it's correct. Okay. Okay. Now this is just okay. Now this is just going to be this matrix X with, I mean, this is going to be in this space, right? U star will bring it here, then it goes here. It's something here. So this has to be, yeah, I mean, it will be like this, right? Vi X Vj star. Okay, Ij. It's again CD cross. I'm sorry. This, yeah, no, it's correct. Sorry, I have written it. I mean, this is what I have written. CD cross. it is matrices here of size. I mean, it's a matrix of D cross D matrix. Okay? And it's a D cross D matrix with entries coming from L of HB. Okay. So this is okay. This is fine. Okay. So UX U star is just this with with a matrix of matrices, matrix containing matrices. Okay. This is VAJ here with I J ranges from 1 to D. 1 to D. Okay. It's a D cross D matrix with the entries VIX VJ star, which is a DA, which is a this. Okay, DB cross whatever. L of HB. Okay. Okay. Now, what is the partial trace of this? Now, the trace A, we want to take the trace A of that. Okay. Trace A of this UX U star. It is just the sum of the diagonal entries, which are precisely summation VI X VI. Okay. So, this is what we want to prove, which is equal to phi of x. So, we have proved it. Okay. So, this is what we want to prove. We want to prove that, oh, this is the trace with respect to the first entry. Sorry, this is trace with respect to the first entry. Sorry. Trace C. The second entry is just taking traces on the individual matrices. The trace with respect to the first entry is just the summing over all the diagonal matrices. So that's what we are doing. So this is the trace C with respect to UX U star. It's precisely that. Okay? Yeah. So we have proved it. Okay. So this is time spring dilation. This has a very bigger theory. If you have any CP map, then you can dilate to a homomorphism, and so that this sits as some. Then you can project it onto that, and this is available for any completely bounded map also. So that theory is a rich theory, but this is only for finite dimensional. We can use GNS representation to prove this. Okay, some sort of GNS representation by defining some. Using a completely positive map, you can define a GNS representation or something called, the positive definite functions. There is a GNS for positive definite function. So using that, you can get it. So we are not doing that. We have directly done this using matrix. Okay, now I want to again go back to matrix theory. Okay. So these are all some facts which we want to. Okay. So let's forget about this. These are all some facts. We have two Hilbert space, which are two systems, okay, with dimension dA, dB. Okay. And we index the orthonormal basis by numbers 1 up to dA minus 0 up to dA minus 1, 0 up to dB minus 1. Okay. Then this L of HA to HB, L of HA to HB or HB to HA? L of HB to HA, I think, right? HA to HB, HA to HB, right? Let me see. Can be identified with HA tensor HB. And of course, it's clear the dimension is just dA times dB. That dimension is dA times dB. So it's clear it can be identified. And what is the identification? So if you have a x here, okay, then you define the vector of x, vectors in here by what we do is the following. You have a matrix, okay? You have a matrix and you have rows like this. You just take this row, make it a column. You make it next row, make it a column, and just stack it just like that. Okay? You have this matrix, this matrix, this matrix. Bring this like this, bring this like this, one by one. That will be an element. That's what we are doing. Okay. So here the map is the following, such that vec of we define this one first I J. Okay. Where so this is from HA to here. So this should be in A and this should be in B, right? Correct? Matrix unit. This is in HA to HB. So this has to be in A and this has to be in B. Of this is equal to, you just have to write it as J tensor I. That's all. Okay, this is an HA tensor HB. So I have written it correctly. Okay. So that's all. I mean, this is clear. So similarly, if we have a vec of, if x is equal to xi summation xij, these are numbers xij. Here it will be xij, where j is in A and this is in B. Okay, this is in B. That is equal to precisely the same summation xij. Okay. Okay. This can be written in a slightly different form, which will be useful. I haven't defined entanglement. I will define it in the next class. Okay. For some reason, which will be clear in the next class, we call the following vector as one of the maximally entangled vector. Let gamma is a vector in, I mean, when I write A, it is HA tensor HA. When I write B here, it is HB tensor HB. HA tensor HA. At this gamma, it is just gamma is equal to summation over I equal to 0 to dA minus 1 I A tensor IA. The same thing. Okay. This is what is called a maximally entangled. Why is it maximally entangled? We'll see. Okay. This is the entangled vector and it's a maximally entangled vector. So you have to take the summation. Okay. Now we can use this to write that vec. Okay. So vec of any x, if you have a x in L of HA HB, then vec x is equal to, let me write it, let's see, 1 tensor x of gamma. Right? Gamma A is in HA tensor HA. So this should be in 1A. This is also in this takes from sorry, it should be, yeah, this is 1A. This will take it to B. This is 1A, this will take it to B. So this will be in HA tensor HB. Okay, 1A of gamma A. This you can directly verify, right? So you can write that, I mean, from a matrix to that vector form, that, I mean, if you have a matrix from an operator from HA to HB, then you can write that as a vector in HA tensor HB using this. You just have to just write it, right? So this is just 1A tensor X into gamma, which is summation over I running from whatever, okay, I tensor I. Okay. Now this is going to be, X is going to be Xij, I mean, and you can write the X also like that, equal to summation 1A tensor, and here it is I maybe I call it as I prime. I prime. This is I and J. Then there is going to be Xij times I J. I and J. This I J is going to be getting confused because this J is coming in for A vector. This I is coming to, but that doesn't matter. Okay. Now if you take it here, okay, this will only when I prime equal to J, this will survive. Okay, I prime should be equal to J. Then you have I Okay, I prime equal to j, it will survive, and you will get I here. Okay, and I prime is equal to j, that means this is going to be j, and that is what you will get this j here. That is what you will get this j here. Okay, so this will be exactly equal to summation over x. I mean, this j will be, this is I, this will become I prime if you want. I prime, x I prime. Okay, I tensor I prime. If sorry, it's I prime tensor, I prime tensor I prime, yeah. No, it should be the first one. Let's write it without mistake. Okay, and maybe I'll write it as j. This j is coming in the first entry. Okay, j is supposed to be in the first entry. Xij. I mean, this is in A. This is for A. This is for B. Okay. Now this, when you hit it with this, j should be equal to I prime. Okay, summation over I here, and there is a summation over I prime here. Okay, j should be equal to I prime. Okay, and this will become j. Let's take out the I prime. This will become j. Okay, so this is going to be 1a tensor xij times this will be I. Okay, and here it will be that's right. Yeah. Yeah, I think so. Yeah. We need not do that. Yeah. Since does that give the, because our definition is uses that, right? Our definition uses this xij goes to this. Or you just have to verify what it acts on those elementary, I mean, this matrix units. Actually, we don't need all that. You want to verify this. Okay, just verify for this. Verify for this. I prime. Okay, that's easier. Then it's just linear, no? So it's enough. Yeah. Yeah, you don't need to do that. From this, it will follow. Okay. I actually wrote down all these things in a paper, but I forgot to bring. So, okay, this is one thing. The another thing is trace of any x is equal to gamma 1 tensor x of gamma. One tensor x, I mean, this is all happening for only for A. A trace of x A operator, x is in L of HA, HA. There is no B here. L of HA, HA. And another thing I forgot to say, verify for IJ. Let me come to this before that. And also, this is also equal to X transpose. Okay, X transpose, which will be from HB to HA. X transpose tensor 1B. I mean, these are both are from acting on HA here. Okay, one X transpose times gamma of B. For B also, you can write a gamma like that. So, but you will get X transpose here. You can verify this again. Transpose of this will be that. You can verify. These are all one should verify with a pen and paper in a private room. Okay. So, okay. Then I want to say that trace of any x is equal to gamma 1 tensor x of gamma. Okay. No, vec of x only. Vec of x only. These two are same. That's the idea. Okay. See, well, I can give you an exercise. Maybe I will give an assignment in the next class. If you have any orthonormal basis, this is under with the standard orthonormal basis. This gamma is different through standard orthonormal basis. Okay, then you are taking I tensor. But standard orthonormal basis, the entries are 1. If you take the bar of that, that's also 1. But you can take any orthonormal basis, EK, and you can take the bar of the individual entries. That is, you call it as EK bar. Okay? Then you can take EK tensor EK and sum it over K. K is from the same sum. K equal to 1 to n or something. EK tensor EK. You use that as gamma. Okay. Then the same formula will work. Okay. So for that, you can use this. So if we have a U here, so any other orthonormal basis, you can get it from this orthonormal basis by a unitary. Okay. So you will have a U here. Okay. You will have a U here. Okay. That U can be taken here as U transpose, but I mean, that will be like U star bar. Okay. So if you have a U, if you have a U bar tensor U, I will write it precisely. U bar tensor U instead of transpose U bar tensor U, that will give you this EK tensor EK. So you can, there is nothing about this this particular basis. You can take any other basis, but you have to take a bar here. Here the bar is same as that, so you are not using it. Okay. I will come to that. Give that an assignment. So this is something directly you can verify, right? This is something. I mean, this is directly you can verify. X is going to be summation xij. And here gamma tensor gamma. Okay. The second entry is going to make it I equal to j. I mean, this is EI tensor EI. You'll get the you have this ij, right? Ji, right? Okay. Ji tensor 1 here. So you can directly verify. It will be just the summation will be just over I, and you can directly verify. Okay. Now I want to define what is called partial transpose. Partial transpose is just take the transpose in one of them. It is just TA, the partial transpose from L of HA tensor HB to L of HA tensor HB. TA is equal to, if T is a transpose map, wait, this TA may refer to partial transpose or the partial transpose in HA or whatever. TA is equal to T tensor 1. This is a, I mean, if I put a TA, it is like TA tensor 1. Okay. Whatever. This is the transpose in HA, in L of HA. And you just take the transpose in one of them. That's all. Okay. That is, if you have, so this is TA. If you want, similarly, TB equal to 1 tensor TB. Okay. It's a partial transpose. You are taking the transpose in one of them. One thing will be clear. If you have a Xij, okay, matrices where Xij's are coming, I mean, this is a dA cross dA matrix is Xij coming from dB cross dB matrices. Suppose if you have that, then you want to take the transpose in the second entry, right? dB of this is just Xij transpose, right? Each one of them you have to take transpose, okay, which is just 1 tensor TB. That is clear. But what is TA tensor TB? TA tensor 1. Huh? Yeah, Xji will work. Like this is equal to just Xj. Yeah, this is a square matrix. So Xj. I mean, what it actually happens is, see, if you want to write HA tensor LA of HA tensor L of HB, you take all these matrices and arrange it like that. But if you want to consider this representation, you want to write the matrices this matrix, you want to consider this matrix of this form, then you are keeping it somewhere, something like this. You understand what I'm saying? Okay. Which you will understand when you write it as, I mean, when you write it as matrix unit, you will know that. That matrix gets transposed here. Okay. Okay. So this is about partial transpose, partial thing. So let us state another theorem. So okay. See, let me recall here. If you have P is from, let's consider some Mn to RHA, L of HA. I write it in this notation, L of HB is Cp. Then this is determined by a single matrix, okay? P of this one, right? Summation one tensor phi of one tensor phi acting on one tensor phi is from L of HA tensor HA to L of HA tensor HB. So you will get a matrix here. You will get a element here. Okay? One tensor phi of this. What is it? This EJ I want to write. Summation IJ tensor IJ, where I and J are equal from 0 to dA. So you will get only phi here. Okay? So this is equal to summation IJ tensor phi of this IJ. Okay? We called it as P phi or something. Okay? And usually it's called as gamma with theta from A to B or something like this. Okay? Or when we call it, I mean, if it is sorry, something like this, where A to B is okay. Or if it is some later when we have this notation, this will be n. Okay? When we call n as the completely positive map, it will be n. Okay. So I will call it just gamma here. Okay? This gamma, I will call it as gamma. Okay. Okay. So if phi from L of HA to L of HB, Cp, then and HR is some Hilbert space. HR some Hilbert space, some finite dimensional Hilbert space. Hilbert space. Okay. Then one tensor phi for any x in HR tensor HA, HR tensor HA, one tensor phi of x is equal to, let me first write it. You have x here. X tensor 1 1 on B. Okay. Then you have this gamma. Gamma is in 1 tensor gamma. This is 1 on R. I mean, you can see that in the middle there is this A is somewhere. This is HR tensor HA tensor HB. This is HR tensor HA tensor HB. Okay, this is how it will look. It's not something that this gamma you cannot bring here, you cannot bring it here. Somewhere there is some mixing has happened. Okay, this. Then you have that trace of A is in the middle. You just take the partial trace with respect to this. Okay, and then you take the partial trace with the partial transpose with respect to T. Then you take the partial trace with respect to this. Okay, this is partial transpose. Okay. That is what is this. One tensor fields. Okay, this is the technique. Proof. First, you see there is nothing about one tensor phi. You can consider one tensor phi is completely positive map. Then one tensor phi is also completely positive map. Then you can work with that itself. Okay, so it's a. I mean, I'm saying, or one tensor phi. I mean, one tensor phi of any x. You can write this x as some ij tensor, right? I mean, ij, some tensor, some xij, right? Where xij is coming from this HA. Then using linearity, you can prove that. All these things are linear. You can prove it. Okay. So I'm saying that it's enough to prove only for phi. Okay. There is nothing, I mean, you can assume that HR equal to C and enough to prove for only phi. Okay. Because any x here can be written as ij tensor xij. Okay, where ij runs over the dimension of HR. Then for each one of them, this is true. This is just phi of this. You will get a phi of, if you add phi of here, you will get phi here. Okay, and that phi can be written, if something can be proved for that, then by linearity you can take it and you can prove it. Okay, so by linearity, so check. Okay, check this. Okay, enough to prove for HR equal to C. Okay, and one tensor. So one tensor phi is just phi. Okay, it's enough to prove about that. Okay. I will do this verification and stop. Okay. 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 So because we have this matrix here, which determines the CP map, we have this matrix gamma, cap script gamma, which determines this. We use that. Okay. And that is what is here. Gamma is here. Okay. So for ij in L of HA, P of ij, P of ij is equal to, so I mean, phi of ij is here. This matrix is this. Okay. Phi of ij is here. You want to get it. So you want to hit it with I and hit it with j here. You will get the right one. Okay. Phi of aj equal to I, but there is a sum, maybe I prime j prime, whatever. Okay. I, j, okay. I, j. As I said, you can write it like this. I have to get the I there. You have to get the, I mean, you have to hit here. Okay. So I tensor 1. This is 1 on B, right? Okay. Then this gamma. Okay. Then J tensor 1. Is that okay? You want to consider this matrix in phi of ij, this cross product ij, whatever, okay? Matrix product ij. If you hit it with I, this gamma, this I will only, it is going to become 1 with this, everything else is 0. Okay. And if you hit it with J, it will only get the J here. This is in the first coordinate, J here, and everything else 0. You will get only one tensor. I mean, you will get, that is scalar times phi ij only. This is what you will get. This, I mean, this is not a matrix. This is not a n cross n matrix. This is like a vector. This is an, I mean, this is only possible with this Kedron notation. If you use mathematical notation, it will not work. Okay. This is something like, this is basically Cn, I mean, the dual space of Cn. This is Cn, whatever, CDA. This is dual space of CDA. Okay. So, which you write like this. So, once you hit it with this, you will get into, I mean, once you use this and this, you will get only this. You write it, it will be clear. Okay. If you hit with this and this, okay, this is like the inner product. We'll take care. Make the other entries as scalars, and you will only get this in, I mean, a matrix here. Okay, that's what you will get. Okay, but that is clear from that. If you apply I from here, if you apply I tensor 1b here, everything this will become 1 and everything else will become 0. Similarly, if you want if you hit it from here, the first entry, only the, I mean, you will get only the J, corresponding J. There it is the sum, only the fixed I and J you will get. Exactly, it is similar to this. Yeah, similar to, yeah, earlier we wrote something else, but I mean, we arranged it that way. The calculation is the same thing. Okay, so, but him writing as this form, we didn't use this form. We wrote some product and verified it. Okay, but it's all the same thing. Whichever is occurs at that time or whichever is useful, we can use it. Okay. Okay. You can write it like this. Okay. Okay. Now I will. Okay, we have done this, so I erase this. Okay. Okay. Now I claim the following. This is equal to trace of trace with respect to the first entry A of this matrix J A I, okay, J A I tensor 1 gamma. Okay, tensor 1. I mean, if you just use that trace, you can write it as the summation of that. If you use that, it will follow. See, I want to prove that this is equal to this. Okay. So if you, this is just trace A of summation of another I prime, summation over I, okay, whatever it multiplies, I tensor 1, okay, of J I, okay, tensor 1b, tensor this I tensor 1. This is what this trace is like. I tensor 1, and whatever we have tensor 1, there is a gamma here in the middle, and I tensor 1. This is what is the traces, partial traces also. Okay. Now, if you have the summation here, only in the, when you take it here, only I equal to J will pick up. I equal to J will pick up. Okay. So, yeah, I equal to J will pick up, and I mean, sorry, this is I prime. Okay? This is I prime. mean, this I and j are fixed here. They are inside. This is I prime. I prime equal to j will, otherwise it's 0. I prime equal to j. So this becomes j here. This becomes, here I prime, that will become 1. If you take the summation over here, this is over I prime. Summation over I prime of this. This is what, how the trace is defined. Okay. Now, if you take this here, I prime equal to j only, it survives. Otherwise, it is 0. So I prime should be equal to j, and the sum, there is no other sum. Okay, so this will become, the I prime is equal to j. That I prime, this will become j. So this is exactly equal to, you will get that, this will go away. This is just I, tensor 1, tensor gamma, and here it will be j tensor 1. Okay. You get this. Okay. So this is the verification. Yes. Okay. So we have verified, using this, we have verified this. Okay. So this implies trace of any x, not trace of any x, phi of any x. Okay. This is equal to phi of summation xij I j. Sorry, ji, ij is right. Yeah, which is okay. Ij. Okay. I mean, there it becomes ji, which is equal to trace a, because trace is linear, you can take all those things inside. Okay. Summation xij. This is ji, right? Ij has become ji. Here we had ij, that becomes ji. Okay. So I directly write ji. Okay. Ji, tensor 1, gamma, 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 whatever. Okay. So this is basically transpose of this. Okay. So this is become trace A of x transpose, whatever that x transpose, tensor 1 of gamma. And if you take, I mean, if you take the transpose of gamma, gamma is a self-adjoint matrix. Gamma is a positive matrix. Okay. So transpose is same as that, right? Right? Yeah. It's a positive matrix. Okay. Bar is also same. Okay. 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 So because of that, it follows. Okay. So we are verified. Yeah. I have something more to say, but I will say it tomorrow. Already